I don't like to hear my voice that often, so it is good to be here. This is an amazing festival, and I'm impressed and honored to be part of this discussion. And I would like to thank Professor Zunzunwala and all the organizers here, and as I heard in the morning, Young Ansan, for inviting me, and I really look forward to the discussions that follow my presentation also. These are exciting times. Whatever we heard in the morning today is only tip of the iceberg in my view. Our opportunities are enormous. The way we live is going to change. We are actually living through energy revolution, not renewable energy revolution. It is energy revolution. So that's why I have titled my presentation as Enabling the Energy Revolution on the Platform of Solar Energy. My focus is going to be on solar, but obviously there are different components of this revolution. We will discuss what are the technologies that are driving this revolution. And as we heard in the morning, we have to be aware of what are the value drivers. No matter what we say, unfortunately, as a species, human beings are myopic. Unless there is a financial case or a commercial case, over the next 25 to 50 years, nearly 100% of our energy needs will be met by renewable energy. At least 80% should be possible. So these are exciting times. So what does it do? It basically changes the way we live, the way we consume energy, and the way we live is changing. This is why I call this a revolution. Now I will show you two graphs. You know this already. First graph is the graph of learning. What you are seeing is the price of module as a function of cumulative module shipments. It starts from 1974 and goes until today. Okay. Now, what has happened around 2006 and why learning improved? This is the result of economies of scale. This is when China entered the market. Do not discount the impact of economies of scale. That is why whenever we talk about new technologies, obviously they look extremely promising from that point of view. But please remember the goalpost is continuously shifting. State-of-the-art technologies have a significant room to improve. So it is extremely important for any researcher to project what happens 5 years down the line, 10 years down the line, and see if the new technology that he or she is working on makes commercial sense. Most of this has happened on established technology platforms. Yes, there have been some innovations. Most of these innovations have been of engineering type. There is no fundamental system breaking change that needed to happen for module cost to come down like this. Another important chart is this. The second chart. This is a chart of cost of electricity. This is per megawatt hour. You can see that just about 10 years ago, solar was the most expensive energy in this mix I'm showing. Whereas the cost of energy from other sources hasn't dropped that much. Solar at DC level has become the cheapest form of energy. You please give me an example of some other industrial sector where change has been this dramatic in a span of 10 years. It is not possible if you are starting from concept to maturity as industry as a whole. There is something else that is driving this. 10 years is, in a grand scheme of things, is extremely short period of time. Right? So how such a dramatic improvement in performance was possible in a short period? Answer is very simple. Solar value chain is an adaptation of the mature semiconductor value chain. In most cases, the inventory of knowledge that existed in the semiconductor industry had to be tailored and adapted for the solar application. So there was no need to reinvent the wheel. So I just want to explain what I am telling you right now. I'm focusing on actually only the front end of semiconductor technology, where you make substrate wafers, because that is relevant for solar energy generation. First, you start with the production of silicon-containing gases. It is a chemical process. By chemical vapor deposition, polysilicon is actually produced, primarily using TCS. In some cases, silane is used. This polysilicon is crushed and melted in quartz crucibles, and single crystals are grown. In the semiconductor industry, crystal growth is the most differentiated actually segment, because defect engineering becomes extremely important, because unless you control defects, it is not possible to maintain Moore's law. But these crystals are then actually sliced by so-called diamond-coated wire slicing. Traditionally, it has been slurry slicing, but it is a wire slicing process. Then, these crystals are, these wafers are subjected to various chemical and mechanical processes. Okay, and in some cases, they go through actually additional processes such as chemical vapor deposition to put a pristine actually layer of silicon for defect-free applications. And there are actually processes where you have to do some layer transfer. I don't want to actually go into details of it. Why I'm mentioning this is because if we look at the solar value chain, at a fundamental level, actually, I want to argue there isn't anything different that is happening, which wasn't already established in the semiconductor industry, particularly in upstream processing. You produce silicon-containing gases the way actually you did in the semiconductor industry. Polysilicon is produced the same way. Polysilicon is melted and crystal is produced the same way. Wafer is actually produced in the same fashion. And then obviously when you make cells, it goes through various actually thermal processes and wet processes. All these unit operations have been established to their maturity in the semiconductor industry for a long period of time. CVD, PECVD processes, which are extremely important, both in the production of PERC cells or coming cells such as TOPCon and heterojunction, are very old processes. So most of the research had to be only applied research here, right? This is why you see such a dramatic drop in the cost of energy. And I have seen this in this industry. When the modules were actually selling at around $6 to $7 per kg, simply by bottoms-up analysis, we had predicted that actually they would sell at around less than 50 cents. This was more than 10, 12 years ago. Today, they are selling at around 21 cents, barring price fluctuations of polysilicon, right? So now what has happened is that if you look at the maturity versus time, we are seeing the second S-curve. Traditionally, an industry starts very, very slowly. Then as learning improves, it goes through inflection point, reaches maturity. In some cases, actually, it dies out. But the blue curve here is the maturity versus time curve for the semiconductor industry. Now, when solar industry picked up, the same knowledge base allowed second S-curve to emerge. And we have not seen the end of it. And this S-curve is very short. And that's why we have seen, quite frankly, a miracle in last 10 years. Okay. Second question is, where is the limit? Okay, LCOE has come down significantly. Now we have applied our knowledge from the semiconductor industry, and there have been some innovations in solar industry. But where is the limit? I can tell you, there are both evolutionary and revolutionary opportunities still available in energy generation. First, let me talk about low-risk options. I will not go into all the details. In the first node of polysilicon, Siemens actually process is the standard. Now, so-called fluidized bed process, which is far more energy efficient, which uses highly reactive gases that can be converted to 100% to silicon, it has been established already. This technology is not freely available, but it is an established, mature technology that works. It consumes one-third the energy consumed actually in the Siemens process. And cost of production is also around 25% lower. Capital requirement is around 25% lower. We'll go to the next node, crystal growth. The state of the art today is Czochralski process. It is a semi-batch process. But the next evolutionary change is going to be continuous Czochralski. This also will actually reduce the energy consumption. This also will reduce the cost by around 20 to 25%. This also will require lower capex by 20 to 25%. And this is more or less an evolutionary change, just like what I showed you in polysilicon. As far as cells are concerned, today, PERC cells are dominating, as you very well know. I have seen this industry, which moved from multi to mono, aluminum BSF, from aluminum BSF to PERC, then actually PERC to TOPCon and heterojunction. Now there is a debate between TOPCon and heterojunction, but I can tell you, both solutions, we should actually lump them into N-type solutions, because PERC uses P-type wafers. N-type actually solution is coming, capex is coming down quite dramatically, cost is coming down quite dramatically. This is also more or less established technology. Right now, actually, it is just scaling up, and economies of scale and supply chain maturity will actually bring the cost and capex down for these technologies. But then there are some high-risk options. Now, you saw this entire actually complex solar value chain. By directly using silicon-containing gases and producing single wafer, reduces around 2.5 nodes in the entire solar value chain. This looks attractive on paper because you are eliminating 50% of polysilicon production. You don't have to make polysilicon, you don't have to grow crystals, you don't have to make wafers by diamond-coated wire slicing and lose around 30% of polysilicon again. But this has its own challenges. Today, I don't have time to go into the details, but most definitely, this is a high-risk option that can potentially reduce capex and further reduce cost of generating electricity. Now, the most exciting research that is happening in solar energy generation today is in perovskites. You all know that perovskites are organometal halides whose optical and electrical properties can be manipulated by adding impurities. One of the reasons why standard actually single junction silicon cells cannot actually have very high efficiency is because they can absorb only part of the solar spectrum because of the band gap. Now, by manipulating perovskite, which is transparent, you can create perovskite silicon tandems. And you can absorb actually much broader actually section of the solar spectrum, and you can go up to 32, 33% energy efficiency. Heterojunction and TOPCon theoretically can go about 28%. On Earth, theoretical efficiency of single junction silicon solar cell is around 29.3 or 4. But with perovskite and silicon tandems, you can break that. Already in laboratories, numbers north of 30% are reported for silicon perovskite tandems. But this is a high-risk option. Okay? So if we look at what is present, what is the midterm option, what is long-term, we all know what is present from polysilicon all the way to modules. We use Siemens process for polysilicon production. Crystal growth happens by Czochralski process. Diamond-coated wire is a standard. PERC cells are dominating the market. And modules are continuously improving. There isn't much technology there, quite frankly. In midterm, there is a potential for FBR to emerge and gain the market share. Only problem with this technology is that it is highly protected, quite complex. Recharge Czochralski will become continuous Czochralski. And slicing will remain what it is, and most definitely N-type wafers are coming. PERC is not going to disappear, but most definitely N-type wafers are going to gain market share. In the long term, I have already actually mentioned, there is a direct wafer technology available, which will impact all the nodes up to slicing. And as far as the cells and modules are concerned, perovskite silicon tandems are the hottest property. What does this all mean? Please look at this table. Present cost of producing energy at the module level. This is cost per watt. Only looking at the cash cost. Forget about margins and polysilicon price fluctuations. It is around 16 cents per watt today in China. Now, with all the technologies I mentioned, only considering low-risk options, we will go to 12 cents. Look how ridiculously low contribution from polysilicon, crystal growth, and wafering is becoming. It's about 2 to 2.5 cents. Maximum contribution is still coming from technically least differentiated node, that is modules. This is one thing actually that we should remember. Cost doesn't mean value. Okay, but in the end, we are looking at 12 cents, quite frankly, even 10 cents per watt module. And for this, I have not even actually taken into account TOPCon, taken into account these perovskites, silicon perovskite tandems, direct wafer, all these high-risk options. So what I would like to actually state is that module cash cost can be actually as low as actually 10 to 12 cents. Margins are approximately 15 to 20% at the sector level. So modules can sell at 15 cents if this is the cash cost. DC LCOE will be less than 2. It can be as low as 1.5 cents. What does it mean? Right now, actually, for us to have round-the-clock AC level solution, number one priority should be finding the right storage solution. Already there is a very clear path. If battery actually capital cost comes down to $100 per kilowatt hour, I think storage LCOE can be only around 2 to 3 cents. That actually gives us 5 cents per kilowatt hour round the clock AC power. This will completely change the game. And I want to say once again, this is only a question of when, it is not the question of if, right? With that, I would like to end my presentation.